Hello, today we will be presenting control systems, and our team is formed by Daniel, Karen, Manuel, Carlos, and myself, Raul. Alright, so let's get started. In order to understand control, we have to understand that there's control in our everyday, daily basis, right? In our daily activities, since we always have needs to cover. Let's take a look at an example right here, real quick. Let's take a look at driving, for example. You need to be able to control this because if you couldn't control this, you would have an accident. There would be a lot of accidents in the road, and it wouldn't be so easy to travel now, would it? On the other hand, we are all part of a certain system. For example, nature, the universe, and ourselves, human beings themselves, right? A system is defined as a set of interrelated elements to fulfill a common purpose. Okay? So let's just say that all everything that's connected into a system of control, there has to be elements that are connected to each other, from the entry point all the way to the exit, the output. Now let's take a deeper look at what a control system is. I've already provided you guys with an example on the last slide. But now let's take a look what a control system is. It is defined as a set of components that can regulate their own behavior or that of another system. The purpose of a control system is to achieve through manipulation of the control variables a domain over the output variables so that these reach values. So in other words, what we want is to have a process in order to be able to control our output, okay? That's what we want to change, our output. Control systems have vast areas of application in transportation, industries including aerospace, chemical and biological processes, mechanical, electrical, and electromechanical systems. Now, can we take a deeper look at this? Of course we can, right? How can we have a control system in electricity? Well, you could probably just put a timer in your lights so they can go out in a certain amount of time, right? And there you go, boom, you have a control system. And you can also look at this as in processes and manufacturing in industries, economic and political and social systems. How do we see this in economical, political, and social systems? Well, you have mathematical problems that can actually predict the outcome. There you go, that's the keyword, outcome. And you can predict outcomes of the economy, right? How? Well, you take an input, you have a process, and there you have an outcome. Okay, so now let's talk about a thermal system. Okay, this system consists of a source of heat, a heat transfer medium, and a temperature detection device, and a control instrument. Okay, the classical thermal applications of renewable energies such as low temperature solar thermal energy for domestic hot water or swimming pools, as we all know, just like showering, or you have a jacuzzi and you could get in there. So the same is not the case with emerging technologies such as geothermal, which has a great potential as it is a highly distributed resource. Now let's take a look at a quick time lapse from the last century having to do with control systems, okay? Well, it is important to say that the first stage of control wasn't until 1990. But before that, water clocks were already made. Where? In Egypt, Greece, and China. After that, well, we have this certain time that's called a pre-classical period, which englobes a period of time from the 1900s all the way to the 1935. And what do we have here? We have feedback controllers. All right. So from 1909 to 1929, instruments were mainly used for these couple of reasons: measurements, indications, and recording. Why is that? Well, measurements has always been an essential instrument on since man has made certain stuff like buildings, pyramids, right? And in 1911, Elmer Sperry created the automatic ship steering mechanism, which consists of regulating vessels in disturbance situations caused by the oceans. In 1922, Nicholas Minorki presented a clear control analysis involving the positioning of the control system and formulated a law of control with feedback. And in 1935 all the way through 1960, it is considered the classical period. 1935 and 1940, during this period, advances in the understanding of analysis and design of control systems were made independently by groups of different nationalities. Modern control, and after 1955, between 1948 and 1952, Richard Bellin worked in the mathematics department of the RAND Corporation. This work allowed him to formulate the optimization principle and dynamic programming. The International Federation of Automatic Control, other known as IFAC, was officially consolidated on September 11 and 12 in 1957 in Paris. Now, after this era, it is where it gets interesting because the development of modern control was significantly boosted by the use of the digital computer during the 1950s and 1960s. In the 1950s, control systems, Eggman promoted the concept of automation with the popular image of mechanization of manufacturing. The evolution of control system is taking place faster and faster, that is, in shorter and shorter periods of times. More and better devices are developed. And don't we see that on our daily basis right now? Like, for example, 10 years ago, do you remember that smartphone that came out? Well, right now it doesn't sound so smart, right? And it's only been 10 years. So, yeah, we don't know what's ahead of us. We don't know what awaits us. In 1972, Ko Kikuchi defines the concept of tronic mecha, which is a union of mechanical and electronic engineering to improve and automate products and processes in Yaskawa, Colombia. Other words, tronic mecha is just mechatronic, engineering of mechatronic. All right? And this is what we have until now for our further career. What are the components that make up a basic control system? Well, in this case, we have three, which is the actuator, the transducer, and the controller. The actuator, the only thing that it is that it works in order to transform energy, and we can compare it in this case to hydraulic or pneumatic or electrical energy in order to realize a function which will generate in effect a new process. This receives a certain signal from the controller, and its function is to give a certain element another signal in order so that it can activate. The transducer, it basically is just an element that transforms the effect of a physical cause, which is to say that it takes a variable from the input and it produces an output from other nature. Okay, the controller, the only thing that a controller is, or what it does more than anything, is to compare the variable within the process in order to have less of an error in its output. Okay, so it is closer to a value of 0. Now let's move on and let's look at the difference between the systems that I mentioned before. As I recall, we had a open loop system and a closed loop system. Now let's take a look at the difference between these. All right. So the first one is an open loop system. Now the difference between this is that in an open loop system does not give feedback. And the difference between a closed loop system is that it does. This one, it is like the process of a blender. It blends, and after that, the process is completed. It ends without feedback. They are not compared to the controlled variable with a reference input. Okay? Now, let's take a look what the difference is to a closed loop system. And I mentioned it a couple of seconds ago, where it has a feedback. It works in such a way that it makes the system refeed. The output returns to the beginning to analyze the difference, and in a second option adjusts more, like this until the error is a zero. Just like I mentioned before in the controller. What it tries to do is it tries to minimize the error on the second try and the third try and so on. In conclusion to everything that was said, all I have to say is that the production in companies and such things as daily tasks has changed just because of the behaviors in the control systems, where their components are duly related to each other, in which the human being has no intervention, right? So, what is this to say about this? Is that day by day we are seeing just a whole new revolution. These systems today are efficient, but with the passage of time, they will continue to advance and advance and advance and innovate more. I see no limit towards this. Minimizing the margin of error more and more on our everyday or necessities or tasks that we need. So, what is there to say? Let's just wait and see what the future awaits us.